Hello everyone, welcome to AJJ Engineering. Today I would like to discuss with you about how to design a mold under mold technology. Introduction. The basic function of a mold is twofold. Firstly, it should impart shapes to the part, and secondly, it should cool the molded part. The number of cavities mainly depends upon the production volume requirement, but it is also related to the size and weight of the parts, which in turn determines machine capacity required. It is also important to design a mold that will safely absorb the forces of clamping, injection and ejection. Furthermore, the mold layout should be balanced, which will ensure proper filling and dimensional control. The mold designer should be very familiar with the processing information properties of the plastic material. The mold determines the size, shape, dimensions, finish and physical properties of the final part. Sometimes the aesthetic requirement also decided the type and position of gate and the type of ejection, etc. The following factors must be considered before starting the actual design of a mold. Deciding the type of mold. There are several types of injection molds in use today. They are two-plate, multi-plate mold, hot runner mold, insulated hot runner mold, hot runner manifold, stack mold. A two-plate mold has got only single daylight, one opening. All basic designs of injection molds have this design thought. A two-plate mold is the most reasonable type of tool to use for part requiring large gates. A multi-plate mold has got more than one daylight. In this design, it is possible to separate the runner system and the part as the mold opens. Multi-cavity with back feeding is also possible. In a hot runner mold, the runners are always kept in molten state. There is no runner wastage and no gate wastage. The cycle time is less and uniform temperature can be maintained and hence uniform properties. The insulated hot runner is a variation of hot runner mold. In this type runner, the outer surface acts like an insulator for the molten inside material. In this insulated runner, the material inside remains molten by retaining its own heat. Sometimes a torpedo or a hot probe is added for flexibility. This type of runner is suitable for multi-cavity center gate parts. The size of the runner is almost twice the diameter when compared to the cold runner system. The hot manifold is a variation of the hot runner mold. In the hot runner mold, the runner plate is heated, whereas in the hot runner manifold, the runner, sprue, gate, etc. are heated by inserting cartridge heaters inside them. A stack mold is a multiple two-plate mold with the mold one placed on the top of the other. This construction also can be used with three plates, hot runner and insulated runner mold. A stack mold construction doubles the production from a single machine. The machine will require additional short capacity. Evaluating the design of the part. The design of the component firstly depend upon the intended use and secondly the limitation of the injection molding process. The properties of the plastic material and the engineering aspect of the mold construction are the additional factors. As a result, the designing of the injection mold require not only a thorough understanding of plastics property but a complete awareness into the problems of injection molding and mold design. The part designer has to consider various molding problems which will greatly influence the design of the mold. Firstly of all, whether the part can be made by injection molding depends upon the flow property of the material. Very long flow paths, large surfaces or very thin sections may result in incomplete molding. The designer also has to consider the shrinkage of the material. Shrinkage is the dimensional difference between the mold cavity and the part after cooling. The degree of shrinkage depends upon plastic material, processing conditions and the product shape. Moreover, there is a shrinkage difference between inline and across the flow direction. Curved, grooved or uneven surfaces are preferred than flat surfaces. Flat surfaces always warp after molding. This warping can be prevented by providing ribs, but ribs can cause seam mark. All the corners should be rounded to prevent the chance of cracking and also to increase flow. The thickness of the part should be kept minimum and as uniform as possible. This will make sure minimum material usage, less cycle time, uniform shrinkage, uniform filling of part and less chance of internal stress. When change in thickness cannot be avoided, then it should be made gradual. Ribs can be added to increase strength to thin wall. If the purpose of the rib is only to reinforce the wall, then its height need not be more than 3 times its wall thickness. The maximum rib thickness also to be limited to 2/3 the thickness of the wall it reinforced. The length of the flow path possible also depends on the wall thickness of the material. For most of the materials, the length of the flow path is proportional to the square of the thickness ratio within the range of 0.5 mm to 2 mm thickness part. For example, rigid PVC has an approximate flow length of 100 mm for 1 mm part thickness. If the thickness is increased to 1.5, the flow path will increase to 1.5 divided by 1 into 2 into 100, that is 225 mm. Selecting the number of cavities. Once the part has been made suitable for injection molding, the next step is deciding on the number of cavities. The various factors to be considered are production volume and delivery time, cost per part, type of gauge, shape and size of of the part, machine capacity, dimensional tolerance. A proper selection can be made only after comparing the advantages and disadvantages of single and multi-cavity molds. Advantage and disadvantage of single cavity mold. Advantage: it is easy to manufacture and the cost is also less. Parts are always identical. Process controlling is easy. It gives better control in design. Disadvantage: it is not cost effective in high volume production. Underutilization of machine in the case of small components. Long delivery time. Production stops when one cavity is damaged. Advantage and disadvantage of multi-cavity molds. Advantage: high volume production, faster delivery time, full utilization of machine. Production can continue even if one cavity is spoiled. Disadvantage: very expensive, difficult to manufacture, non-uniform cooling, non-identical parts, less flexibility in design. Calculation of number of cavities. Usually the number of cavities is desired by the customer, but from the molder's approach, the number of cavity can be found out as given below. Based on short weight. Generally short weight, yes, is taken as 85% of the short capacity of the machine. If W is the weight of the molding, then the number of cavities NC is equal to S by W. Problem: calculate maximum number of cavities possible on a SP30 machine for a part having 10 gram weight. Short capacity of the machine is 36 gram. Effective short weight 36 into 0.85 equal to 30.6. Maximum number of cavities 30.6 by 10 equal to 3.06. Since no fraction is possible, the maximum number of cavities can be 3. B. Based on the plasticizing capacity. If P is the plasticizing capacity of the machine, SM is the number of shots per minute, and W is the weight of the component, then the number of cavities is NC is equal to P by SM into W. Generally, 85% of the plasticizing capacity used for calculation. Problem: calculate the number of cavities possible for the above part based on plasticizing capacity. Plasticizing capacity for SP30 is 17 kg per hour and cycle time achievable is 6 seconds. Plasticizing capacity is equal to 17 kg per hour equal to 17 into 1000 divided by 60 gram per minute equal to 283.33 gram per minute. Effective plasticizing capacity 283.33 into 0.85 which is equal to 240.83. Number of shots per minute 60 by 6 equal to 10. Material required or minimum for a single cavity of mold 10 into 10 100 gram per minute. Therefore, the number of cavities possible 240 divided by 100 equal to 2.4. Since no fraction is possible, number of cavity possible is only 2. C. Based on clamping force. The clamping force required to keep the mold closed during injection must be exceeded the clamping opening force. Generally, the cavity pressure is taken as 25 to 45% of the injection pressure. The clamping pressure required is given by the product of the cavity pressure and the total projected area of the component. Sprue and runners. Minimum clamping force is equal to projected area into cavity pressure. Problem: calculate the number of cavities possible on SP30 machine if the common diameter is 50 mm. Injection pressure required is 1200 kg per centimeter square. Projected area 3.14 into 2.52 is equal to 19.634 centimeter square. Cavity pressure 1200 into 0.45 which is equal to 540 kg per centimeter square. Clamping force required for single cavity 540 into 19.634 which is equal to 10.602 ton. Considering the 30% safety factor, 10.602 T into 1.3 is equal to 13.783 ton. Clamping capacity of the machine 30 ton. Therefore, the number of cavities possible 30 by 13.783 which is equal to 2.17. Since no fraction is possible, the number of cavity possible is. By carefully controlling the cavity pressure, it is possible to use machine with a lower clamping force. In other words, with the same clamping force, more parts can be produced at one time using a multi-cavity mold. The calculation by normal method is not accurate because the cavity pressure is always assumed. Cavity pressure can be accurately measured by placing the pressure transducer or estimated using flow molding techniques. The actual pressure depends on the following factors: resistance in the runner and gate, temperature of plastics, viscosity of plastic, distance of the plastic from the gates, the flow rate of the resin. Advantage of measuring mold cavity pressure using pressure transducer are fast molding, optimization of initial machine parameters, recording the mold cavity pressure, shortened startup times as the effect of machine adjustment can be known immediately, faster startup time with predetermined machine parameters. Molding conditions are now defined by the established temperature and pressure profile. Since trial and error method is not required, the startup time is reduced. Optimized setting result shorter production cycle. The cavity pressure profile gives a good indication of happening inside the cavity. A better revealing of the injection pressure allows more accurate adjustment of the machine, resulting in increased productivity through shorter cycle time and reduced energy consumption. Less tool modification. The decision to rework a tool can be made on the basis of dependable measurement and not a guesswork. Mold modification in some instances can be avoided by using pressure control injection. Lower clamping force. By carefully controlling the mold cavity pressure, it is possible to use a machine with a lower clamping tonnage, fewer mold release problems. Excessive cavity pressure generally causes ejection problems. By carefully controlling the injection pressure, it can be minimized. Improved dimensional control. The dimensional correctness of the part directly depends on the cavity pressure. Controlling the pressure in cavity results in better dimensional repeatability. Uniform part weight. The cavity pressure has a direct influence on the weight of the molded part. With a tighter cavity pressure control, very close tolerance on the part weight can be achieved. Some cases it results in considerable material savings. Mold production. Controlled cavity pressure result in lower mold stress, less distortion, reduced wear and longer tool life. Consistent part quality. Internal stresses caused by the difference in set point temperatures and pressure can degrade the part quality. This can be eliminated by early detection and taking corrective measures. Less rework. Excessive pressure can result in flash and burr on part. This also can be avoided by timely intervention. More economical production with fewer and less skilled personnel. Maximum production with few unskilled operations can be achieved by eliminating all possible problems by constantly monitoring the cavity pressure. Other factors affecting the number of cavities are location of mold cavities, layout of the mold as decided by the product design, quantity requirement in a family mold, component assembly or packing requirement, indexing requirement for multicolor and multi-material components, deciding on the mold material. Steels play a very important role in the manufacturing of mold. Its property like hardness, toughness, tensile strength, abrasion resistance, wear resistance, etc. are very suitable for mold construction. Steel is very easy to machine and various surface finish operation, polishing, coating, etching and texturing can be very easily done on it. Its dimensional stability and low coefficient of linear expansion are essential factors in controlling the part dimension. Other materials used are aluminum, beryllium copper, upco alloy, etc. Aluminum is preferred for short run molds because of its high machinability and cooling efficiency. Beryllium and upco alloys are used as inserts when high emphasis is given for lower cycle time. The factors to be considered while selecting material for mold elements are mold life, mold quality, plastic material, reinforced, corrosive, etc. Surface finish required on the part, machinability, hardness, cycle time, material cost, material availability, plating, photo etching and coating requirement, lead time, mold manufacturing. The below table will give an idea about what kind of material can be used for different mold elements and its hardness, which was given equivalent different standards are listed below. Deciding on the strength requirement for mold. The force involved in molding operations are compressive. They are exerted by the external mold clamping force and the internal pressure exerted by injected material. The mold cavity must withstand the forces created by the plastic material during injection. These forces are very high and can be around 1400 kg per centimeter square and even more in thin wall molding. These forces are also cyclical. Under cyclical loading, the allowable stress the steel can withstand is 10% below the yield stress of the mold material. Strength requirement of a mold plate. Since most of the mold plates are fully supported, calculation is limited to the core backplate only. We know that M by I is equal to S by Y or M is equal to S by Y into I. M is equal to momentum of resistance, I moment of inertia, ES bending stress, Y distance from the neutral axis, Z section modulus. We also know that in the case of a beam, the bending momentum at the center of the beam carrying a uniformly distributed load is M is equal to WL square by 8, which is equal to WL by 8, where W is equal to uniformly distributed load, capital W is equal to total load the plate can support, L is equal to length between supports. Contact area of support rail and support pillar. One important feature, contact area of the support rail and support pillars. Steel mold will begin to crush if the unit clamp pressure exceeds 1.5 ton per centimeter square. In less severe cases, the plate may get distorted loading into parting line flash. So the stress on this area should be such as to prevent embedding of these blocks into the plate. The safe tonnage that a mold base will take as far as the support rail are concerned can be calculated in this way. The weakest section of the support rail is the clamping slot area. Let us consider 446 into 596 standard mold base. The width of the support rail is 56 mm and the width of the clamping slot is 15 mm. The area will be 56 minus 15 or 41 into 596 into 2. Since there are two blocks, area into allowable stress which is equal to compressive force. The allowable stress for low carbon steel is 2 ton by centimeter square. Thus 4.1 centimeter into 59.6 centimeter into 2 into 2.t per centimeter square, which is equal to 977.44 T. The support rails can withstand a compressive force of 977.44 tons. The addition of support pillar will also increase the compressive force in production with the area they provide. Thus, a 50 diameter pillar would add the following force. Area of 50 mm pillar 3.14 into 2.52 cm square, 19.625 cm square. Compressive force is equal to 2 into 19.625, which is equal to 39.25 tons. When the support rail or support pillar dimensions are changed, they may sink into the plate. Clamp tonnage and mold size. If the mold base size is too small for the clamping force, it may sink into the platen of the machine. The platen impressions are dangerous because they reduce the contact area for the mold for another mold, thereby increasing the chance for further indentation. These indentations may further lead into the cracking of the platen. Generally, all the machines have provisions for reducing the clamping force. Nevertheless, we should recognize the danger and specify the limit in which it is safe to operate. Most of the platens are made of cast steels. The permissible safe working load is 0.5 ton per centimeter square. Considering the safety factor of 7, with this information we can calculate the safe working limit for the particular mold base size. The force involved in molding operations are compressive. They are exerted by the external mold clamping force and the internal pressure exerted by injected material. The mold cavity must withstand this problem. A mold 250 mm into 300 mm is to be loaded in a 500 ton machine. The diameter of locating ring is 100 mm. Find the permissible operating tonnage. Also calculate the minimum area of mold base needed to absorb 500 ton clamping force. Minimum area of mold base needed to be absorbed 500 ton equal to 500 divided by 0.5, which is equal to 1000 centimeter square. Area of mold base given 250 into 300, 75,000 centimeter square, which is equal to 750 centimeter square. This shows that the mold should be operated at a lesser tonnage. The permissible operating tonnage is given by tonnage equal to centimeter square minus register ring area into 0.5. 750 minus 78.5 into 0.5, which is equal to 333.75 ton. To protect the machine platen against the damage, it is better to check contact area of the mold and the platen to see that the safe working limit is not exceeded. Placing support pillars. If the space between the support rails is long enough, the injection force may deflect the core plate or the core back plate. Such a deflection will cause the flashing of the part. To avoid this problem, the gap is reduced by placing support pillars. The diameter and the spacing pillars can be calculated using beam formula. Maximum bending moment M at the center of simply supported beam subjected to uniform distributed load. W equal to WL square by 8, which is equal to WL by 8. W equal to total load. M is equal to S into Z. S is equal to M by Z. Therefore, stress at centers S is equal to WL by 8Z, where M is equal to total load the platen can support permissible load. L length between supports. Z section modulus. S allowable safe stress. The section modulus Z for a rectangular plate is given by the formula. Z is equal to BD square by 6, where B is equal to width of the plate, D is equal to thickness of the plate, S is equal to allowable safe stress. Problem. A mold base of 300 into 400 into 50 mm core back plate is supported by spacers of 40 mm width. Calculate the permissible load on support pillars and permissible projected area of the impression. Maximum allowable bending stress is 845 kg centimeter square and safe concentrated stress cavity pressure is 500 kg per centimeter square. First, we will calculate the section modulus of the core back plate. Z is equal to BD square by 6. Z is equal to 40 into 5 square by 6, which is equal to 166.67 centimeter cube. Stress center S, which is equal to WL by 8Z. 845 is equal to W into 200 by 8 into 166.67. Where length, which is equal to 300 into 2 into 40, which is equal to 220. W is equal to 845 into 8 into 166.67 divided by 22, which is equal to 51213. When the material is injected, the cavity will exert a concentrated pressure on the support plate. For this condition, a safe concentrated stress in compression of 500 kg per centimeter square is allowed. Since the safe stress and the load are known, the area can be calculated. We know that stress is equal to load by area. 500 equal to 51213 divided by A. A is equal to 51213 divided by 500, which is equal to 102.5 centimeter square. Hence, the total area of the back plate can only be 102.5 centimeter square. If this area is less than the projected area of the molding, then it denotes that additional support pillars are required to withstand the stress. If one row of support pillars is added, the L dimension is 110 mm, thus doubling the load capacity of the plate and also doubling the permissible molding projected area to 205 cm square. If you maintain the same permissible stress of 500 kg per centimeter square, increasing the number of rows of support pillars decreases the distance between the resting points of the beam, thereby increasing the area of the concentration pressure of cavities. Approximative values of allowable stresses for steels are given below. First column talks about material, tensile strength, stress repeated, stress reversed. Strength of the cavities. The maximum deflection commonly allowed is 0.125 to 0.25 mm depending upon the size of the tool. Of this, 0.1 to 0.2 mm may be because of the clearance between the inserts and pocket and elongation of the bolster. For calculation purpose, a maximum deflection of 0.025 to 0.05 mm is generally taken. The approximate thickness required for the sidewall may be calculated from the following formula. T is equal to 3 into square root of CPD raised to 4 divided by EY, where T is equal to thickness of cavity wall, C is equal to constant, P is equal to maximum cavity pressure, T is equal to depth of the cavity wall, E is equal to modulus velocity of steel, the maximum allowable, Y is equal to the maximum allowable deflection of cavity wall, value of constant C. The value of C depends on the length of the cavity wall to the depth of the pocket. Value of C we can see in the table based on the L by D ratio. Problem. Calculate the minimum wall thickness required if the cavity depth is 100 mm and cavity length is 300 mm. Cavity pressure 500 kg per centimeter square. Maximum deflection is allowed is 0.03 mm. Where we know that T is equal to 3 into square root of CPD raised to 4 divided by EY. L by D is equal to 300 by 100, which is equal to 3. Therefore, C is equal to 0.134. T is equal to 3 into square root of 0.134 into 500 into 10 raised to 4 divided by 2.1 into 10 raised to 6 into 0.003, which is equal to 47.30 mm. Sprue runner gate and vent design. The design of gate, runner and vents has been a mystery ever since Haier invented the injection molding machine. Nowadays, the design is mostly done with the help of software which are 80 to 90% reliable. But using some simple formula, 80% of accuracy can be achieved. Sprue. In single cavity mold, the sprue usually enters directly into the cavity, in which case the sprue diameter at the point of cavity entry should be approximately twice the wall at that point. Insufficient sprue gate diameter can cause excessive friction, burning of plastic at the gate area. Too large sprue diameter requires a prolonged cooling time. The cooling fountain should be installed directly opposite to the gate to avoid hot spot. The usual approach to solving sprue problem is to design a shorter sprue, use a hot sprue, or eliminate the sprue altogether. Runner design. In conventional mold, runner should be designed in order that the runner is short, free from bends, equal runner length in multi cavities, minimum cross section. The following table can be used as general guideline for selecting the runner diameter. The runner diameter should be specified based on the runner length. Then working towards the sprue, runner diameter should increase with each 90-degree turn the runner makes. Figure A shows a type of two cavity mold. The total length of the runner from the part to the sprue is only 75 mm. So from the table we see that for ABS material the runner diameter required is 2.38 mm. In the runner system shown in figure B, we find the length has increased to 150 mm. For that length from the table we see that the runner diameter should start at 2.76 at the gate, going towards the sprue, but we find that it takes a 90-degree turn before reaching the sprue. So we should increase the diameter by 20%. Therefore the diameter should be increased to 3.30. But in this there is one more runner merging with the main runner. So the main runner in this case has to be increased by 40%. So the main runner diameter should be changed to 3.86. Figure C shows a different layout with two secondary runners. The total runner length is 250 mm. So the starting diameter should be 3.96 mm. Two increases of 20% are necessary for each runner because of each has 290 turns. We must again add 20% for both incoming runners. So finally the main runner diameter is 6.65 mm. Alternative rough method. The runner diameter can be roughly calculated using the formula given below. For less flow index material, the 25% should be added to calculated value. The runner diameter is equal to weight of the molding raised to 1 by 2 into length of the runner raised to 1 by 4 divided by 3.7. Gate design. The gate has three critical components, namely depth, width, and length. Depth is the most important factor because it determines how fast gate solidifies. The depth of the gate can be 40 to 90% of the wall thickness. When using an easy flow material, it is best to use the lower percentage. Width of the gate should be 2 or 3 times the depth. Again, for easy flow material, it can be 2 times the depth. If part is larger than 100 mm, think of adding another gate. The land dimension should be half of the gate depth but never more than 0.75 mm. Excessive land will cause jetting and other molding problems. Insufficient land will cause sigma mark near the gate area. Vent design. Vents are probably the most ignored and mistreated part of the mold. Yet, vents can do more to lower injection pressure, reduce cycle time, eliminate stress, burn marks, and minimize warp and shrinkage than any other single element in mold construction. Vents allow trapped air or built up gas by resin melting to escape from the closed and sealed mold into which molten plastic is injected. If the air is trapped inside, it will result in short molding and sigma. The table below lists the recommended vent depth for runner and the cavity for different materials. Consider lower value for easy filling area and higher value for difficult filling area. It is just as important to vent the runner as it is for cavity. Normally the runner is vented to twice the depth of cavity because it is is not a problem if there is little flash on the runner. In fact, flash is an indication of proper vending. Vending should be equal to 30% of part perimeter. If the runner is vended, only 20% of the parting only need to be vended. Vent should be placed equal on both sides of the length of the runner and cavity. Vent width can be from 6 mm to 12 mm. It can be made less than 6 mm for small parts but never more than 12 mm as the material may sink and close the vent. It is also necessary to relieve the vent leaving a land of 3 to 5 mm. The relief depth is made to 0.1 mm. As far as possible, the vent should be ground. Rules for vending. Vent to suit an anticipated flow of material. Vent at the closed end of all pockets. If the pocket machined from a solid, vent pin must be provided at least the deepest location. Whenever possible, provide moving vent pin. Vent should be as deep as possible without causing flash. All rib bottom should be vented. Every vent must lead to outside. Recommended vent for cavity and runner as given below based on the material. Component retention. One of the important decisions required while designing is how to retain the part on the side where you have planned injection. The part during opening can be retained on the required half by applying the following methods: relying on the stringaging of the mold, by modifying the parting line, by providing undercut, by reducing or increasing the draft, by varying the surface finish, by using side course, by using lifters, by using push pins, by using air poppet, by modifying the design.